Kia ora, everyone, and welcome. Today, we are unpacking a massive concept sitting right at the heart of modern AI, and that is parallelization. We're going to use first principles thinking here. We'll break this pretty complex tech down to its absolute bare essentials, and then just rebuild it step by step together.
So, right off the bat, I want you to think about a super common experience. Have you ever typed a prompt into an AI, smashed enter, and then just sat there, watching that blinking cursor? It makes you wonder, right? Why do these incredibly smart AI agents sometimes take absolute ages to answer what seems like a really simple request? Honestly, it can be incredibly frustrating. Now, the natural assumption is usually that the AI is just, thinking really hard, or the math is just way too complicated. But if we strip this right back to the foundation of how these workflows actually operate, the real culprit is usually just how the AI organizes its to-do list.
Okay, so let's strip away all the tech jargon, the code, the algorithms, all of it. Let's look at the absolute irreducible truth of the matter. The fundamental first principle here is this. Doing tasks one after another takes longer than doing independent tasks at the exact same time. Now, I know it sounds incredibly obvious when you say it out loud, doesn't it? But this single truth is the absolute foundation of the parallelization pattern. If tasks literally don't depend on each other, well, forcing them into a single file line is just a massive waste of time.
Let's use a real-world analogy to really ground this. Think about putting down a classic Sunday roast, or, prepping a hang yi. If you used a strictly sequential approach, you'd put the lamb or the pork in to cook, and then you'd literally just sit there waiting for hours for it to completely finish before you even started peeling a single spud. I mean, that's absurd, right? No one does that. The parallel approach is what we actually do in the kitchen. You get the meat cooking, and while that is happening, you prep the potatoes, boil the peas, whisk up the gravy all concurrently. You do those independent tasks all at once to get dinner on the table way faster.
Right, so let's move over to the tech space and see how this concept builds. A basic, sequentially programmed AI agent operates exactly like that terrible cook who waits for the meat to finish before touching the potatoes. It does the hard yakka just one painful step at a time. So, if it needs to research a topic, a sequential workflow means it searches source A, waits for the result, summarizes it, and then only then moves on to search source B, waits again, summarizes, and finally puts an answer together. The latency here, that is the waiting around for external databases or APIs to actually reply, it just adds up at every single step, creating a massive, massive bottleneck.
But what if we apply our first principle instead? In a parallel AI workflow, the agent is smart enough to identify which tasks are independent. Searching source A doesn't actually require knowing the result of source B, right? So the agent searches both sources simultaneously. It asks for all the information at the exact same time. Then, once all those independent concurrent lookups are complete, it brings the pieces together to synthesize the final answer. Just like cooking our Sunday roast, this parallel approach completely fixes that latency bottleneck because we aren't just standing around waiting in line.
And you can really see exactly what happens under the hood here. Notice how a single input comes in on the left and is instantly distributed to 3 separate subagents. They are completely independent of one another. The overarching system doesn't have to wait for subagent 1 to finish before it triggers subagents 2 and 3. The time it takes to get all 3 outputs back is essentially just the time it takes for the slowest individual task to finish, rather than adding up the time of all 3 combined. It's brilliant.
So you can see how this architecture fundamentally changes the entire flow. Following the parallelization pattern, the user provides a prompt, and the system immediately branches out. It triggers multiple AI agents, or tools, or API calls, whatever they may be, that fire off simultaneously. They do all their work side by side, their outputs get aggregated, and the final result is returned to the user in an absolute fraction of the time.
Section 1. Smashing common AI misconceptions.
Now, as we build up our understanding here, it's really crucial we don't carry any false assumptions with us. When people hear the word parallel, they often assume the computer is literally using multiple physical brains to do the work simultaneously. But the truth, especially when we're coding these agents in Python, is actually much cleverer. Python uses a library called asynchronous, and because of this quirky thing called the Global Interpreter Lock, or GIL, Python code generally runs on a single thread. So it's not actually processing things simultaneously on different processors. Instead, it uses an event loop for incredibly smart task switching. If one task is idle, say it's just sitting there twiddling its thumbs waiting for a web page to load, the system instantly pauses it and switches to another task. It's exactly like a chef who stirs the gravy while waiting for the oven timer to ding. It creates the effect of multiple tasks progressing at once, completely slashing latency without needing some massive, expensive supercomputer.
Section 2. Parallel AI in the real world.
Okay, so now that we have a solid grip on those irreducible truths, that concurrent independent tasks save time, and that we can achieve this through really smart task switching, let's see how this works out in the wild. The practical uses are everywhere, making apps feel sweet as and lightning fast. In data processing, an agent can run sentiment analysis while simultaneously categorizing customer feedback. For content generation, it could draft an email body, write the subject line, and find a relevant image all at once. But honestly, my favorite example is the travel planning agent. Imagine you're planning an epic Kiwi road trip. You ask the AI to sort out a weekend in Queenstown. Instead of checking flights, then checking hotels, then checking events one by one, the Parallel agent fires off requests to all those APIs at the exact same time. You get a complete, multifaceted itinerary presented to you incredibly fast, purely because the AI didn't wait in line.
To actually build these systems, developers rely on specific frameworks. You can kind of think of these as advanced toolkits that let the AI cook multiple things at once. Two major players here are LangChain and Google's Agent Developer Kit, or ADK. While they both achieve that ultimate goal of parallelization, they do approach it slightly differently. LangChain relies heavily on its expression language, combining runnable objects. Google ADK, on the other hand, provides robust mechanisms for a main agent to delegate tasks out to multiple specialized subagents.
Let's look at a really concrete example straight from the source material for LangChain. Developers use a cool construct called runnable parallel. Imagine you feed the AI a topic, something like, the history of space exploration. Using runnable parallel, the system can trigger 3 distinct chains at the exact same time. One chain writes a summary, one generates 3 interesting questions, and one extracts key terms. These chains just run side by side, fetching answers simultaneously. Once they're all done, a final synthesis prompt scoops up the summary, the questions, and the terms, and generates one comprehensive output for the user. It's super tidy.
And Google ADK tackles this beautifully using what they call a parallel agent. The source material outlines this fantastic multi-agent system for researching sustainable technology. Basically, a main coordinator delegates tasks to 3 specialized AI researchers. One researcher is instructed to scour the web for renewable energy sources. Another looks exclusively at electric vehicles, and the third investigates carbon capture methods. The parallel agent orchestrates all 3 of them to run concurrently. They go out, do their hard yakka, and store their findings. Only when all 3 are completely finished does a final merger agent step in to synthesize their independent findings into a single, highly structured report. It's incredibly efficient.
Section 3. Summary. From basics to clarity. You know, it is pretty amazing how complex architectures ultimately boil down to such simple logic. Let's briefly recap the journey we just took. We started with that simple truth of a Sunday roast. Don't wait for independent tasks to finish sequentially. We learned that by applying this parallelization pattern, whether through LangChain's runnable parallel or Google ADK's parallel agent, we are literally just executing independent operations concurrently. As our source material perfectly summarizes, parallelization helps reduce overall latency and makes agentic systems more responsive for complex tasks. By utilizing that clever task switching while waiting for external resources, we eliminate those agonizing wait times and create AI systems that feel truly, instantly responsive.
So, we've broken it right down to the studs and built it back up. Now, it's your turn to apply this first principles thinking. Look at your own digital life or your business processes. Where are you acting like that sequential AI, waiting for step 1 to finish before starting an entirely independent step 2? If your tools, and your own mind really, didn't have to wait in line, how would you speed up your own workflow? I highly encourage you to take this foundational approach and use it to decode other complex topics. Thanks so much for joining me on this explainer, and I'll catch you next time.